Have you ever gazed up at the night sky, captivated by the twinkling stars? Among these celestial wonders, hidden from casual view, are meteorites, remnants of distant worlds that have journeyed across the vast expanse of space to reach our planet. These space rocks, often mistaken for shooting stars, offer a tantalizing glimpse into the universe's enigmatic past. But what exactly are meteorites, and what secrets do they hold within their ancient structures? Imagine holding a piece of a comet or asteroid, a fragment of the early solar system that predates our planet. That's essentially what a meteorite is. These celestial wanderers have embarked on journeys lasting millions, even billions of years, carrying with them clues about the formation and evolution of our solar system. Their composition, structure, and even the stories etched within their very atoms offer invaluable insights into the universe's grand cosmic drama. Join me as we delve into the fascinating world of meteorites, unraveling the mysteries locked within these cosmic time capsules. The journey of a meteorite begins in the cold depths of space, where fragments of asteroids or comets, remnants from the solar system's formation, drift through the cosmos. Sometimes their paths intersect with Earth's orbit, setting the stage for a dramatic entrance. As a meteorite enters the Earth's atmosphere, it encounters friction, generating intense heat that causes the meteorite's outer layer to burn and glow. This fiery descent, often visible as a brilliant streak of light across the sky, is what we call a meteor or shooting star. Most meteoroids burn up completely during their atmospheric plunge. However, some survive the fiery descent, making it to the Earth's surface. These survivors, the meteorites, are what scientists eagerly seek out as they hold invaluable clues to the universe's history. Upon impact, meteorites can leave behind craters, some small and others vast scars on the Earth's surface, testaments to the immense energy released during their arrival. These impact sites serve as reminders of the dynamic and ever-changing nature of our planet and its place in the cosmos. Meteorites, much like the planets and moons they originate from, are not uniform in their composition. They can be broadly categorized into three primary types, each with unique characteristics that reflect their origins and formation: stony, iron, and stony iron meteorites. Stony meteorites, the most common type, are primarily composed of silicate minerals, resembling rocks found on Earth. This category is further divided into chondrites, which contain small, spherical grains called chondrules, and achondrites, which lack these primordial grains. Iron meteorites, as their name suggests, are primarily composed of iron-nickel alloys. These meteorites originated from the cores of large asteroids that underwent differentiation, a process where heavier elements sink to the center, forming a core. Stony iron meteorites represent a fascinating blend of the previous two types, containing a mixture of silicate minerals and iron-nickel alloys. These meteorites likely formed at the boundary between the core and mantle of differentiated asteroids. Each type of meteorite provides unique insights into the processes that shaped our solar system. Studying their composition, structure, and even the magnetic fields preserved within them allows scientists to piece together the history of our cosmic neighborhood. Unlocking the secrets within. A glimpse into meteorite composition. The true beauty of meteorites lies not only in their cosmic origins, but also in the intricate details of their composition. These space rocks are like time capsules, preserving within them a record of the early solar system's building blocks. By analyzing these components, scientists can unravel the mysteries of our cosmic past. Silicate minerals, primarily olivine and pyroxene, form the bedrock of most meteorites, particularly the stony variety. These minerals are also abundant in our planet's crust and mantle, hinting at a shared origin in the early solar system's protoplanetary disk. Metallic elements, primarily iron and nickel, are another key component of meteorites. While iron meteorites are almost entirely composed of these metals, stony meteorites and stony iron meteorites also contain varying amounts. These metals provide clues about the differentiation processes that occurred in larger asteroids and planets. Chondrules, small spherical grains found embedded within chondritic meteorites, are among the oldest objects in our solar system. Their presence provides valuable information about the conditions and processes at play during the solar system's earliest stages. Organic compounds, including amino acids, the building blocks of proteins, have been found in some meteorites. These findings suggest that the ingredients for life may have been delivered to Earth and other planets by these celestial messengers. Volatile elements, such as water and carbon dioxide, are typically found in trace amounts within meteorites. These elements provide clues about the composition of the early solar nebula, the cloud of gas and dust that eventually coalesced to form our sun and the planets. Isotopes, atoms of the same element with different numbers of neutrons, are like fingerprints, providing a unique signature for different solar system bodies. By analyzing the isotopic ratios in meteorites, scientists can determine their origin and trace their journey through space. Radioactive elements, such as uranium and thorium, act as cosmic clocks, decaying at a predictable rate. By measuring the ratios of parent isotopes to their daughter products, scientists can determine the age of meteorites and, by extension, the age of the solar system. Echoes of creation meteorites as time capsules of the solar system. Imagine holding a 4.5 billion-year-old rock, a relic from the very dawn of our solar system. That's what meteorites are, tangible pieces of cosmic history that have journeyed across time and space to reach our planet. By studying these celestial messengers, we gain invaluable insights into the processes that shaped our solar system and its inhabitants. One of the key revelations from meteorite analysis is the confirmation of the nebular hypothesis, the prevailing model for solar system formation. The presence of chondrules, those tiny spherical grains found in some meteorites, supports the idea that our solar system formed from a rotating disk of gas and dust that gradually coalesced into planets. Meteorites also provide clues about the conditions that existed in the early solar system. For example, the presence of certain isotopes in meteorites suggests that our sun was enriched with heavy elements from a nearby supernova explosion, a testament to the interconnectedness of celestial objects. The diversity of meteorite types reflects the dynamic processes that shaped our solar system. The differentiation of larger asteroids, evidenced by the presence of iron and stony iron meteorites, highlights the role of heat and gravity in shaping planetary bodies. The discovery of organic compounds in some meteorites has fueled speculation about the origins of life on Earth. While not conclusive proof, the presence of these building blocks suggests that the ingredients for life may have been delivered to our planet from space, a tantalizing possibility that continues to intrigue scientists. By analyzing the composition, structure, and age of meteorites, we gain a deeper understanding of the processes that led to the formation of our sun, the planets, and ultimately ourselves. These space rocks are like pieces of a giant jigsaw puzzle, each piece contributing to a more complete picture of our cosmic origins. Windows to the past unveiling Earth's history through meteorites. Meteorites not only illuminate the early solar system's history, but also provide invaluable clues about our planet's evolution. By studying these celestial visitors, we gain insights into Earth's formation, the composition of its interior, and even the potential triggers for significant events in its past. The composition of certain meteorites, particularly chondrites, is remarkably similar to the Earth's mantle, the layer beneath the crust. This similarity suggests that both Earth and these meteorites formed from the same primordial material in the early solar system, providing clues to our planet's building blocks. Iron meteorites, with their high metal content, offer insights into the Earth's core. These meteorites are thought to represent the remnants of differentiated asteroids, where heavier elements sank to the center to form a metallic core, much like what happened during Earth's formation. Some meteorites contain evidence of past water alteration, suggesting the presence of liquid water on their parent bodies billions of years ago. These findings support the idea that water, a crucial ingredient for life, was present in the early solar system and may have been delivered to Earth by asteroid and comet impacts. The impact of large meteorites has shaped Earth's history in dramatic ways. The Chicxulub impact, believed to have caused the extinction of the dinosaurs 66 million years ago, serves as a stark reminder of the potential consequences of these cosmic collisions. Yet such impacts may have also played a role in delivering water and other essential elements to our planet, contributing to the conditions that made life possible. By studying the composition, age, and impact history of meteorites, we gain a deeper understanding of Earth's geological past, the processes that shaped its surface, and the potential role of extraterrestrial impacts in its evolution.